Okay, welcome to our first recorded lecture for thermodynamics. We are beginning the topic of open systems or control volume analysis, which is chapter 4. We've covered 1, 2, and 3 and had exams 1 and 2 through that material, so we're going to cover chapters 4 and 5. Chapter 5 will be our introduction to second law analysis. And then we'll have exam 3. Then we'll talk a little bit more about second law applied to open systems in chapter 6 before the final exam. So still to come exam 3 and the final exam. Before I start talking about open systems, however, let's talk about exam 2, which has been returned to you by now. So hopefully you have your exam as I go through the solution. And then we'll get to chapter 4 topics. 31 students, the average was 77.3. The median was 87 though, so half of you made more than an 87. I think there were 13 A's on the exam. Good job everybody on this exam. The first problem is your properties. So you had some sample exams given to you, so you should have been prepared for a problem just like this. So every row corresponds to a state. So the first small chart here is dealing with refrigerant 134A. I gave you H as 250 for the first one, which happens to be between the saturated liquid and saturated vapor values for H at 25 bar. So it turns out to be a saturated mixture. Use this number to calculate the quality and you'll get a quality of 0.737. Then you can subsequently calculate what V is. So V is 0.005365. So you had to remember that for VF on the chart, actually that's not true. I don't know if that's the case for this on the chart. Let me go get the chart and take a look quickly for the refrigerant. At 25, yes, this number is times 10 to the minus 3, right? So this is actually 0.001056 for the saturated liquid value. The saturated vapor value is 0.0069. Okay, so since we're looking at this now, we can come in with H is equal to 250, and you'll see that it's in between 269 and 168. So that's how we identified that we're in the saturation region. The temperature will be this exactly 77.59. So please copy down 77.59 and don't even round that. There's no reason to put 77.6 there. I know it's really close. 77.59 is the temperature. Quality ended up being 0.73 like we talked about before. So that's the first state for the refrigerant. The second one was at 6 bar. The temperature is 125. So let's go back to the same chart. At 6 bar, the saturation temperature is around 20. So we're at 125, so we're in the superheated region. So now we're going to go to the 6 bar chart here in superheated. Right here, and go down to 100, and we don't have 125, we have 120 and 130, so it's the average. It's the average of these two numbers for a row of 125. So that ended up being superheated, and here are the numbers associated with those end results. Then we transition to look at water. For the first case, you're given 30 bar and 120 degrees C. So if we go to the water tables, I'm going to go to the 30 bar in the water tables. First, if we go here to 30 bar, the saturation temperature is 233.9. Temperature given to us is 120, so we're well below that. So we are a compressed liquid or a subcooled liquid. So VF is VF at that temperature of 120. So now I'm going to go to the temperature tables, find 120. VF is Remember, we have to move the decimal point here again. 120, so it's 0.001063 exactly. No need to interpolate for that. And then to find h, that was a little bit more challenging. For that h, remember that calculation of h is equal to h of the saturated liquid plus Vf times the pressure minus the saturation pressure. So we have this extra little contribution for an incompressible substance. Okay, so HF, we can get that right off of the charts. VF, we already have V. The pressure is 30 bar. The saturation pressure is 1.985 bar. And then we have to remember that these units have to be converted. So you have to leave bar, put it in kilopascals, and then this will end up being in a kilojoules per kilogram equivalent. And so there's a small adjustment of about 2 or 3 actually because of this term. So the correct answer is 506.68 for H. Some of you use the compressed liquid water table, so I'm going to go find those quickly. For water, the compressed liquid water tables are the very last tables. So after the superheated tables, this is page 935, you have compressed liquid water. Some of you did a double interpolation off of this table. I did not expect you to do that, and in general we're not going to use this table in class because it's so easy to assume incompressible and just use this formula here again. Okay. The next problem is you're given a temperature of 120 and a specific volume is given. This specific volume is larger than Vg at 120, and so it ends up being superheated. So you then have to go to the superheated tables. For the superheated tables for this one, you have to look for where is V equal to 1.188 for a corresponding temperature of 120. And so that was a little bit challenging to find that, but so I'm just going to peruse through the pages here that you can't see yet. I'll show you when I find it, and check what is V at 120. And I'm going to find V just perusing the tables. I actually found 1.188 exactly in this case for a pressure of 1.5 bar. So no interpolation needed for this one. To get U and H, the values are here directly, and the pressure is 1.5 bar. Next one is also superheated. Now you're given a pressure that's very, very high at 320. It ends up being superheated again. 320 is actually, that pressure is not in your saturation tables. This is above the critical pressure. And if you remember, for numbers that are above the critical temperature or pressure, you just assume superheated. So if you go look in superheated tables, there actually is a column corresponding to 320 bar. 320 bar, and then the specific volume is 0.011055. So I'm going to go into 320 bars here, and I'm looking for 0.011. Let me see the number again. There, you can't see it, it's in the shade still. There it is, 0.011055. Up here I have 0.01150, so close but not the same. So the number is actually less than that. So it's in between these two. So it's not at 600 and it's not at 640. It turns out that it's the average of those two. So the temperature ends up being 620, and now the U ends up being the average of these two, comes out to be 3134.9. Okay, so those are your pure substances, and then you had two states corresponding to an ideal gas to calculate. So you needed R for air. Molecular weight for air is 28.97. Universal gas constant 8.314. The only other thing to kind of be careful of is that the units of this is kilojoule per kilogram K. The final unit for R, that kilojoule is a kilonewton meter, and a pascal, which shows up in pressures over here, a kilopascal, is a kilonewton per meter squared. So if you're careful with the units, then when you use the ideal gas equation of state, PV equals RT, right? This is the R that goes right there. You need to make sure that that is in an absolute temperature, so K, and that's in an absolute pressure, so not a gauge pressure there. So in the first example, you're given a temperature and a pressure. You can substitute exactly into this equation to solve this for V. You'll get 0.8499, and then to get the internal energy, specific internal energy, this is dependent on the temperature, so you have to go into the ideal gas tables for air at 300 K. Ideal gas tables for air at 300 K. So U is 214.7. This is the U column, this is the H column. 214.07 kilojoules per kilogram. Now for the next state, you are given a specific volume and you're given H. Remember, H and U are both dependent on the temperature. So with this H value, we can get the temperature. So we need to go looking for through the tables for 705.1. 705.1. Here's the H. I'm going down. Here's 702. Here's 713. So it's in between these two, right, for our H value. The temperature for these columns over here is 690 and 700. So there's a temperature column here, right? So these columns over are a continuation of the temperature. So the temperature goes down over here, down to 440. It starts again at 450 on this side and continues down. Some of you actually did the interpolation and went all the way over here to 390 something, 392 I think it ends up being, when it should be 692. So after the interpolation, you get 692.4. You can then take specific volume and temperature, substitute in the ideal gas equation to come up with your pressure is 397.4 kilopascals. Okay, so for the grading, all of the numbers here are 6 points apiece, with the exception that this one, which took the extra calculation, got a little bonus point, and then identifying the appropriate phases were 3 points apiece. And that'll end up totaling 100 points. The second problem was a closed rigid tank that contained water. So it's closed and rigid, so the volume's not changing, so we know right away this is, and the volume and the mass are not changing, so the specific volume is going to be a constant. So that's kind of our special kinematic constraint, and this V2 is going to be equal to V1. The mass is given as 0.5 pound mass of water. The initial state, T1, is given as 100 degrees Fahrenheit. The quality is 0.3945. You're given a quality of 39.45% for state 1. Then it says identify or determine the heat transfer to raise the temperature to 700 degrees Fahrenheit. So at state 2, the temperature will be 700. And then it says also find the pressure of the water at state 2. So they only give us the temperature at state 2, but if we recognize that the specific volumes are going to be the same. So V2 equals V1, and V1 we have two properties, so that's defined. So actually I put a little star here. Both states are now defined. I went ahead and calculated V1 with this quality, right? And I ended up with 138.08 cubic feet per pound mass, so that's also V2. So now these two numbers define state 2. So we're asking now to find the heat transfer and the pressure at state 2. State 2 is now defined, right? So with those two properties, that ends up being superheated. No interpolation was needed. So that ended up being 5 psi. To get Q, you do an energy balance. Q minus W equals delta E, which reduces to M U2 minus U1 specific internal energy here. So those are linked directly to the state, so we can come up with those two numbers. There is no work in this problem, no wires, right? No moving boundary, no shaft. There's no mechanism to do any work in this problem, so that's going to be 0. So Q is just equal to M delta U. Since the states are defined, we can now go get the two values. The first one, the quality is given, right? So 452.86. The second one was superheated. Ends up being 1256.5. Substituting in numbers to that, you get 401.82 BTUs. So you see all these little numbers that I have in circles everywhere. That one should be circled. All those add up to 100%. Communication was 20% for this problem. So this is what I used for the grading rubric for this problem. Some of you missed this connection, the closed ridges. Some of you actually tried to calculate a work and then use the work in this one. There is no work. Problem 3, there is work in problem 3. 2 kilograms of air are in a piston cylinder assembly. Okay, so here's my piston cylinder. Its air mass is 2 kilograms. At state 1, they give us a temperature and a pressure, and then the air is heated at constant pressure to a new temperature of 900 degrees C. So T2 is 900 degrees C. Pressure was a constant during the process, so P2 is the same as the first pressure, P1, 200 kilopascals. So it is being heated, so I should draw, I'm going to add to my drawing there Q. Some Q is entering, so that'll end up being a positive number. The work during the process, we need to find the work during the process in kilojoules and the heat transfer in kilojoules. We're neglecting change the kinetic and potential energy. Okay, so for the work, it's a constant pressure process, so we need to integrate PdV. So it reduces simply to V times the volume change. The states are defined, so we can get specific volume, and mass is given, so that gives us a connection to get to these volumes. I just made a substitution that volume is mass times specific volume and factored out the mass. Most of you got to this expression fairly easily, so now we just need to evaluate properties. It's an ideal gas, so V equals RT over P. Right, this is the same R that we used for problem number 1. V1 ends up being 0.53545. V2 with the same equation ends up being 0.6834. So substituting these numbers into our equation, we end up with 459.18 kilojoules for a final answer for the work. To get heat transfer, we can now do an energy balance. So the first law of thermo says Q minus W equals, again, M times U2 minus U1, neglecting kinetic potential energy. Delta E reduces to this. We have an expression for the work, so I'm just going to algebraically solve this for Q, take W to the other side. Both states, again, are defined, so we can now do the work necessary through the charts at the two temperatures given to come up with U1 and U2, and then substitute into the equation. The final answer is 1744.8 kilojoules. And once again, for the grading rubric, all of these little plus numbers here are the values for each of the components in this problem. I think I have them all there. That should all add up to 100. Your short answer problem. Identify an isotherm on a PV diagram. So the isotherm on a PV diagram is the one that goes down and to the right. You had to identify the saturated vapor is everything on this line. Saturated liquid is everything on that line. Where those two come together at the peak is the critical point. Compressed liquid is on this side of the wet dome. Superheated is on the right side of the wet dome. Next question, why is compressed liquid alternatively called a subcooled liquid? You can use whichever term you want, but the reason for that is if a compressed liquid, the temperature is always below the saturation temperature. I got different answers for this one. All I really want you to say is that the temperature is less than Tsat to get credit for that one. The quality of a saturated vapor is, okay, so saturated, it's all vapor, it's going to be 1. Saturated liquid would be 0, saturated mixture, anything in between. The equivalent critical properties for air are given. There's a critical temperature and the critical pressure. The compressibility factor for air at 152.95 and a pressure of 3,205 kilopascals, so a very high pressure and a low temperature. What is the compressibility factor? Okay, so to get that, you needed to get the reduced temperature and the reduced pressure. The reduced temperature is the temperature divided by the critical temperature. The reduced pressure, the pressure divided by the critical pressure. And I gave you both of those numbers. So you'll end up with 1.15 and 0.85, and then you needed to go to figure A1 on page 985 and use the generalized compressibility chart. I'm going to look for that now. Although I have a different page, so we need 0.85 and 1.15. So here's the chart. Here's 0.85. 1.15 is here. So they intersect on this line, so I can follow this line out and I get 0.8. Compressibility factor is 0.8. So if you were close to 0.8, I gave you credit for that. And I gave you half credit if you had the wrong number there, but still indicated you knew to do something with the reduced temperature or reduced pressure. Finally, true and falses. A two-phase liquid vapor mixture with equal volume of saturated liquid and saturated vapor has a quality of 0.5. The answer to that is false. Quality is the mass ratio, percent mass of vapor, not the percent volume. The properties of velocity and elevation are not influential in the specification of an intensive thermodynamic state. That's true. You cannot use or relate those physical properties to the intensive thermodynamic properties, and so they do not influence the state. So that statement is true. The next one, for a simple compressible substance, values of any two randomly chosen intensive thermodynamic properties fix the state. This one is kind of tricky because key is this word any. If you just randomly pick any two, it doesn't necessarily work. For example, if I give you temperature and internal energy for air, that doesn't work. Those two are dependent on each other, so that will not define the state. Same thing if you have a saturated mixture and I give you the temperature and the pressure, those two are dependent, and so that will not define the state. So the answer to this one is false, and I gave you two examples of how that's the case. For an ideal gas, specific internal energy and temperature are not independent properties. Okay, that was one of the examples I gave you for the case right up above. This is true. They are not independent properties. For air at a particular temperature, the specific internal energy only has one possible answer. It is completely dependent on the temperature. And finally, the generalized compressibility chart applies to all gases. Yes, that's why it's called the generalized compressibility chart. So the answer to that one is true. Okay, so there's also the weighting of each of the parts of this one as well, given over on the left. Okay, so if you have any questions about the grading of your test, you can still contact me and we can talk about that if you think that I have overlooked something. in the grading of your test. Okay, so now let's move on to talk about the next topic in chapter 4, which is open systems. And so open systems means that mass is now crossing the boundary. So the system is just kind of our general term that we'll use to say this is what we are deciding as an engineer to analyze. And now mass is crossing the boundary. The example I give you of that is one that I think is interesting to me, so that's why I use this example, a jet engine. I think you all can kind of visualize a jet engine. Air enters the front of the jet engine, is compressed through a compressor. Then in a combustion chamber, fuel is added, and a lot of energy happens through a chemical reaction or the burning of fuel. And then high energy gas now passes over a turbine. Some of the energy is taken out of that air through the shaft power required to drive the compressor. So this is an internal rotating shaft. The rest of that gas now enters an augmenter, or so basically an open pipe here, and then it is nozzled out the back. So a low density, high velocity gas is nozzled out the back, causing thrust. Right, the velocity of the exit gas is much higher than the velocity of the intake gas, providing a net thrust. So if we think of this device as the volume of everything inside this device, that's what we're going to analyze, a volume now instead of the mass. Then the mass inside is constantly being replaced. Mass is always entering at some rate. Mass is always leaving at some rate. Oh, there's also mass here, fuel coming in. So we're going to do what's called a control volume analysis now, rather than looking at a mass and the evolution of a mass. Instead, we're going to look at a volume and consider both a mass balance and an energy balance as a tool. To keep this in perspective, let's compare this to what we've been doing so far in the class with closed systems. So through chapter 3, we've only considered closed systems. So the mass is, we never have mass crossing the boundary of our system. And so effectively, the system is identified by mass. So all we're doing is saying, hey, here's a chunk of mass that's going to be our system. Let's watch what happens to it over time. We could heat it up. That mass could be doing some work through boundary work. And an energy balance will allow us to equate a state 1 and a state 2. So Q minus W is E2 minus E1. The units of this are a kilojoule, or BTU. It is an energy. So this is what we're doing now, and our new perspective will be to look at a volume and watch and observe the volume as mass passes through. That mass will also carry energy with it, and then we can still have work and heat transfer for the process. But in general, for a control volume analysis, we're going to consider things on a rate basis, because things are happening instantaneously at certain rates. For example, a mass flow rate, we'll put a dot on top of m to indicate a change with time. So m dot is the rate at which mass flows in, or a kilojoule per second, the rate at which mass crosses at an entrance or at an exit of our control volume. Okay, so we've already mentioned the spatial perspective that we're now going to consider. So for an open system processes, so this is what we're saying is now our control volume approach. We're going to have two really different perspectives that we can use now to analyze the system. One will be to treat the device as if it's a steady flow device, which means everything is happening at an even or constant rate. Things aren't changing over time. So steady means steady with unchanging with respect to time. Transient is when things are changing with time. So we're going to need to be able to identify which one of these two systems that we are working with, and we'll have a different set of base equations that are our tools to analyze, depending which one of these two this particular problem that we're solving corresponds to. So the I'm going to give you the final answer of the equations that we're going to use to analyze these types of problems, and then I'm going to go through and derive them, just trying to give you an indication of where we're headed with our theoretical development. Once we have developed these equations, then we'll be ready to work some examples. So these are kind of our analysis tools. So for the first category of devices, steady open devices, when things are happening steadily, our conservation of mass principle is going to look like this. The rate at which mass enters the control volume minus the rate at which it leaves. These little summations here just indicate that we could have many ports where stuff comes in, many ports where stuff goes out. We have to add all those up. So the rate at which mass comes in minus the rate at which mass goes out has to equal the rate at which mass is left behind in the control volume. So that's dm control volume. This little CV stands for control volume. dm control volume dt. Okay, so the definition of steady means that no extensive property can vary with time. Mass is an extensive property, so if we're looking at a steady flow device, the right hand side of this equation has to be 0. So we're left with an equation that says m dot in equals m dot out. This is a mass balance equation. For conservation of energy, or the first law of Thermo, the equation will look like this. If you notice, Q minus W equals delta E was a closed system energy balance. Now on a rate basis, it's just Q dot minus W dot equals dE dt. If we have mass crossing the boundary, then that mass that's entering brings energy with it. The mass that's leaving takes energy out. And so these two terms represent the advection. If this is an energy per unit mass times a mass flow rate, then this equation ends up equaling an energy per time. The masses cancel between these two. And again, if we're in steady state, energy being an extensive property does not change with time, so the right hand side disappears. So the units of every term in this equation are kilojoules per second or BTUs per second. So these are all rates of energy change rather than an energy. So these two are going to be kind of a new perspective where we're looking at an energy balance on steadily operating open devices like the jet engine we talked about before. For transient devices, an example, let me go ahead and give you an example of a transient device would be filling an air tank. You had a tank that doesn't have much air in it, and now you connect that to a compressor. You can push much more air into that tank. So there's an initial state with some amount of air and a final state with more air in the tank. So the amount of mass in the tank is changing with time. Therefore, it's a transient problem, not a steady state problem. So that would be how we identified that as a transient problem. Just ask yourself, does any extensive property change with time? And if it does, it's a transient. So for transient problems, we're going to analyze that much more like closed systems. And so an energy balance is Q minus W equals delta E, just as before for a closed system, except that the mass that has entered or left during the process, during the entire duration of the process, can contribute to adding or removing energy during the process. So mass carrying a property away into or out of is called advection. So these, I'm terming those the advection terms. And so these are not rates. Notice there's no dots on any of these terms. Right? The units of this equation is going to be energy, and these are all accumulated, an accumulated value during the entire process. Conservation of mass then looks very similar to the one for open steady, except that there's no dots again on any of these. So the amount of mass that's come in during the process minus the amount of mass that has exited during the process has to equal to the change of mass in the system, M2 minus M1. So this M1 means the mass that's inside the volume at time 1. This M2 means the mass that's inside the volume at time 2. This mi means the mass that was outside and is now inside the system, the amount of mass that has moved across the boundary into the system, and this is the amount of mass that has moved across the boundary out of the system. It was once in the system, now it's out of the system. So kinematically, these variables mean something different than these variables for the steady state. So what I want to do first is focus on conservation of mass. We're going to derive those and work some examples and just develop our analysis capabilities for conservation of mass, and then we're going to add balance of energy. I know I can sense that I'm moving fast through these notes, but I'm hoping that you can pause anytime you want to, write down questions, take notes, go back, listen again. And so if this lecture does not go for the entirety of an hour and 15 minutes, I think that's okay. I still want to stop and work per lecture on what my normal pace would be as if we were lecturing live. Okay, so now let's just focus on conservation of mass only. So mass can never be created or destroyed is our principle. We are not worried about E equals mc squared, and that would make a connection between our energy balance and our mass balance. We're still keeping those separate, so no E equals mc squared here. But mass is conserved, recognizing we're not working any problems where relativity is an issue. So let's look at a control volume as our kind of classic example we've always used as a piston cylinder assembly. So that means over time our volume might be changing. And to make it an open system, I'm just going to maybe put a port on this side, like a pipe, that's connected, that will allow me to deliver a mass flow rate coming in. And then the same thing for an exit. There's a mass flow rate that can be going out. And so maybe there's some external devices that are controlling. Maybe there's a compressor over here that's pushing mass in on this side, and maybe this exit over here is just venting to the atmosphere. There's many different scenarios that can set up this situation. But the m dots again represent the rate of change of mass with respect to time, or like a mass speed, right? How fast mass is entering at this boundary. And so a conservation of mass principle would be to say that the rate at which mass enters minus the rate at which mass leaves, that difference is contributing to increase the amount of mass in the control volume. Alright, so that's what's coming in, crossing a boundary to come in, minus the rate at which it leaves, so that what's crossing a boundary to go out, contributes to increasing the mass in the control volume. So the little CV, mCV is the mass in the control volume. So if mn is larger than m out, then m dot CV is going to be increasing, a positive number. Rate of change of mass inside the control volume is this right hand side. Alright, previously I had called that d dt of m in the control volume. Okay, if we are in steady state, right, so mass is flowing through our device at a steady rate, so that means I can't have an increase of mass in the control volume over time. That would make it a transient problem. So m dot control volume is equal to 0. What I'm left with from that energy balance equation is the rate at which mass comes in equals the rate at which mass leaves. So this is the equation that we would use for an open steady device. Let's consider then alternatively, if we had a transient system, well, that would indicate that we had more mass in the system at one time than another time. To evaluate the transient systems, rather than considering an instantaneous rate, we're going to consider the accumulated effect during the duration of a process. So we're going to integrate over time. Alright, so let's integrate m dv over time, and we will end up with, if I the rate at which it's changing integrated over time equals m2 minus m1. You can think of this as dm control volume dt. dt's cancel, and I'm going to integrate dm from time 1 to 2. So at time 1 we have m1 in the control volume, at time 2 we have m2 in the control volume. So the right hand side of our equation is going to turn into m2 minus m1. The right hand side of this equation after we integrate. Right? We're going to then integrate the left hand side of the equation. If I integrate m dot n, right, this is actually m dt, right, dt is going to cancel, so I'm integrating dmn from time 1 to 2, so I'm adding up the mass that's come in during that time. You just get mn, the total amount of mass that has entered during the process. Same thing for here at the exit, you get m out, the total amount of mass that has exited during the process. So mn minus m out equals m2 minus m1. So all of these are masses in this, not a rate. So we have two contrasting equations. These are masses, and up above these are flow rates, so instantaneous measures of how fast mass is moving at particular locations. Before we continue to look at steady flow, actually those are our two equations. Let me give you those two equations that you can kind of memorize, these two equations if you will. So when you're working a problem and doing your analysis, these are equations that you are free to start with without any derivation or explanation needed. Just say conservation of mass and write these equations down. So if it's a steady flow device, you can start with this equation. Summation of m dot n minus the summation of m dot out equals to 0. And if it's a transient, summation of mn minus summation of m out is m2 minus m1. So you see these have dots and these don't, so it's very critical to pay attention to your dots and details of the symbolism that we're using here, and do that in your analysis when you're communicating your work as well, please. Okay, so notice also that for a closed system, I can't have any mass crossing the boundaries, right? So these two have to be 0, so that leaves me with m dot of the control volume is equal to 0, right? So integrate that, says that m dot in the control volume is equal to a constant. So we never talked about conservation of mass with a closed system because it's a trivial concept. There's nothing there really to analyze with. The amount of mass was obviously the same for a amount of mass that we're analyzing. Equivalently, if we look at the transient system and say for a closed system I can't have anything that has come in or left throughout the process, then we're left with our energy balance equation above, m2 minus m1 equals 0. Right, so again, mass is a constant for a closed system. So this really is two different representations of the same concepts, one on an instantaneous rate basis and one on an accumulated basis for analyzing open devices. Okay, so let's talk about how to evaluate m dot at a location. So at what I'm going to use the term port, an exit port or an inlet port. So we're going to talk about the kinematics now at an inlet or an exit port. So I have it written here as an exit port. Sorry, so this is our control volume, and here is a pipe that's carrying mass away. There's some flow rate, mass flow rate, rate at which mass passes through or crosses the boundary right at this location. Okay, so we need a representation for this in terms of the properties of the fluid. So one property of the fluid we're going to consider is the velocity. The mass here has a particular velocity, right, at that surface, at that point. So let's consider a little differential area right on this surface here and draw an enlarged version of that. That particle of material is moving with velocity vector v. That little underline means that's a vector. N is a unit normal vector to the surface, so it points directly away or out of the system. It's orthogonal. I have a little square here is to indicate that this is orthogonally to the cross-sectional area here of our exit, orthogonal to that. So the component of this velocity that contributes to flow exiting is the component of v that acts in the n direction. So that would be v dot n. Just take a scalar product or a dot product of that velocity vector with n. That gives you a scalar velocity that represents the component that's carrying mass out of the control volume. Notice that if I take the dot product or the component of velocity that acts tangential to this surface, that wouldn't be leaving the control volume. We only want the component normal to it. So Vn is technically the velocity dotted with the normal component. So we're only really going to care about this normal component of velocity. The mass flux then, if I multiply the velocity times a density, that gives me a local measure of the mass. If I integrate that over the entire cross-sectional area, that'll give me the entire mass that's crossing through that exit area. So this is an area integral over the exit of rho times the velocity, and I only need the normal component of velocity there. Okay, so this is a general expression which is probably going to be the beginning point for students in fluid mechanics course. In this course, as an intro thermodynamics course, we are always going to simplify our situation, and only consider velocities that are constant and densities that are constant over the cross-sectional areas at a single port anyway. So these are going to be constants and come out front. And then if I integrate dA, you simply are left with the integral of the exit area. So we'll end up with rho times V times area. So our generalized assumption in this class is that we are going to be given a velocity. That velocity is going to assume to be Vn. I'm just going to call it V with an arrow on top like this. This is not a vector. This is a scalar. I'm just trying to distinguish this V as velocity and not volume. Right, okay, so after we do our integration like we've already mentioned, m dot E will be rho times velocity times the area. Right? Rho is the density, if you remember. We don't deal with density directly in this class. Instead, we use specific volume, which is 1 over rho. So our equation to remember is it's the velocity times the area divided by the specific volume. And so that equals m dot at a particular location, whether it's an inlet or an exit. Right? Inlet or exit, that still works. The only thing you have to remember is that each of these properties, velocity, the area, and the specific volume, all are at that same port. These all must be evaluated at the same port, whether it's an inlet or an exit. So there's another equation to remember that's really just dealing with the kinematics of mass flow. So this is, if you substitute in units, velocity times area over specific volume will be a mass flow rate. So in the end, units will cancel to be left with kilojoules per second or pound mass per second. If we just look at the numerator, a velocity times an area, this will be a volume rate, so a volume flow rate. So this is so you can think about representing a flow rate as a volumetric flow rate. Volumetric flow rate would just be V times A, cubic meters per second, or cubic feet per second. To convert that to a mass flow rate, you simply need to multiply by the density or divide by the specific volume. That'll convert that volume into a mass. But you need to be careful in that volume is not a conserved quantity. It's the mass flow rate that is the conserved quantity. So you can't say the volume flow rate in equals the volume flow rate out. That's not necessarily the case. It is the case for mass. So here's our equations that you can memorize now, and we'll use these and work some examples. Now the first one, if you have a steady flow device, This is what's important. The transient device, this is the equation that's important. We'll use, notice the dots here and no dots on these equations down below. To represent the volumetric flow rate, I'm going to put a volume with a dot on top of it for a volumetric flow rate. So this volumetric flow rate is the same thing as velocity times area. So that gives us plenty of theory now, and we can now work an example. The example I'm going to work, actually I'm going to change pages here. Let's work this example first. Okay, so a 3 cubic foot rigid cylinder contains air initially at 70 degrees Fahrenheit, 500 psi absolute. So this little extra A there, psia, means that's absolute pressure. It's air, so we can already make note that this is going to be an ideal gas. An air compressor adds more air to the cylinder until its conditions reach 120 degrees Fahrenheit, 2000 psi. So we're going to put a lot of air into this cylinder at state 2, at which time the inlet valve is closed and the air cools to its original temperature at 70 degrees Fahrenheit. Determine the mass of air added to the tank and the final pressure in the cylinder. Okay, so for this example, first thing we need to decide is, I'm going to go back and look at our equations. Right, we're going to use conservation of mass to analyze this. They're asking us to determine how much mass was added to the tank. Right, which one of those equations up above are we going to use? We need to identify this system. We have a certain amount of mass initially, and then we have more mass at a later time, so that indicates that the mass inside the tank is not constant over time. We are not dealing with a steady flow device in this case. We are dealing with a transient device. There's an M1, we add to the tank, add air to the tank, and then a different M2. Right, so we can identify right away, I'll just go ahead and write down here that this is a transient process. Right, and you can even put the equation if you want. Summation of Mn minus the summation of M exit equals M2 minus M1 of the control volume. Okay, so let's continue our normal analysis steps to work this problem. I'm going to draw a figure of a tank. I don't know why I'm using this as the shape of my tank, but I'm going to draw the sides to look like they are rigid because it's a tank. Right, I'm going to put a valve on top of this. There's a sign from a controls class of a valve. It's just a circle with an X in it that have air inside here. Right, then we're going to open this valve, put some more air in it, and then close the valve. And so they give us some information. We have state 1, the temperature T1 is equal to 70 degrees Fahrenheit. We're dealing with air. I'm going to go ahead and write ideal gas over here. And so I want to convert that temperature to degrees Rankine right away, so I don't make that mistake later. The pressure at that point, P1, is equal to 5,000 pounds per square inch. So that's going to define state 1. I'm going to define a state 2. When they add mass, the temperature goes up to 120 degrees Fahrenheit, so that's 580 degrees Rankine. And the pressure is going to go up to 2,000 psi. So that state is defined, but then they continue the process and say that the air is then going to be cooled down until you get to 70. So there's actually a state 3 in this process. T3 is equal to 70 degrees, so it goes back to the 530 degrees Rankine. Right, and so I don't have another property at this point.
right? P3, I'm not sure what P3 is, right, because that state's not defined. I'm going to put a little star on this one. That state's defined, and a little star on that one because that state is defined. What else is given in this problem? Oh, look, there they give us right there that the volume is 3 cubic feet. Alright, so the volume is constant. Alright, so that's a V1, a V2, and call it a V3. Those volumes stay the same through the entire process. So determine the mass of air added to the tank and the final pressure. So we're going to find M2 minus M1, the mass of air added to the tank, and P3. So that's our problem statement. Okay, so this is normally the point in class when I would be asking for student input so that we can be thinking about this together, but I guess I'm just going to have to outright tell you how to do it. So my first observation is to come up with this P3. I just need one more property at state 3, right? And the transition from state 2 to 3 is actually that little bit is a closed system, right? We've closed the valve here, right? So we closed valve at 2, right? So from 2 to 3, V3 is actually going to be equal to V2 because it's closed rigid, right? So 2 to 3 is closed and rigid. So with that connection, that'll give you another property at state 3 so we can figure out what P3 is. So that's just going to be an evaluation with properties. Right, so we have state 2 defined, V2, so let's put to find P3, V3 is equal to V2, right? Then T3 and V3 define the state, so that'll give us P3. Okay, so we got to calculate V2 first. V2 is equal to RT2 over P2. Right, we can just calculate that and come up with a number, but it's actually, rather than doing that, oftentimes we can just recognize that V3, which is also RT3 over P3 using the same ideal gas equation, remember that these two are equal, so we can set those two equal. Right, RT2 over P2 is equal to RT3 over P3. And then the r's cancel. This gives us a nice convenient expression. P3 is equal to T3 over T2. That's P2, just doing the algebra. This is super convenient because now we don't have to deal with units, go calculate what even R is. R has canceled out of the equation. I just need to take a temperature ratio. Alright, so this is going to be equal to 530 Rankine divided by 580 Rankine times P2 is 2000 psi. These, remember, must be an absolute. Must be absolute. Notice that if we put degree C in here, this ratio is going to be completely different. So that's one of the things that gives away when you need something to be in absolute values, is if you're taking a ratio. But also know that this equation that we're using here was derived from the ideal gas equation of state, which requires absolute temperatures. So this gives us a final P3 of 1827.59 psi rather than the 2000. So what's happening is, as air is added to the tank, all of the friction from the airflow is heating up the gas a little bit until finally the pressure gauge reaches 2000 psi and the valve is closed, but the gas is still at 120 degrees Fahrenheit. Then while it sits there and cools off, the pressure drops down a little bit, so at some time later the pressure is finally going to read, kind of the steady state pressure is going to read 1227.59 psi. Okay, so now we're left to figure out what is M2 minus M1. So we'll do the conservation of mass part. M2 minus M1. We can actually calculate M2 and M1 directly, I think, right? We could get the M from this just from the specific volume, and the volume is given, right? So we can say that, remember that specific volume is defined as a volume per mass, so that would leave us with mass is equal to the volume divided by the specific volume, and then we can apply that at various states. So at state 1 we can do that, and at state 2 we can do that. Alright, so we can use these numbers that we avoided calculating above to come up with those. Okay, but let's go ahead and just make a substitution for those and do as much algebraically before we substitute in numbers as possible. Right, so I'm going to substitute in for that V1, right? V1 is equal to RT over P. Right, so that V1 right there is RT1 over P1. Did I do that right? I did that right. Right. And that at 2 is RT2 over P2. So finally, we're trying to evaluate M2 minus M1. Let's substitute. So I'll have V two over RT2 in the denominator. The P2 in the denominator of the denominator comes to the numerator. Minus, do that again for M1. V1 divided by RT1 times P2. So we can substitute in numbers anytime you want here. I'm going to go ahead and say that velocity is constant. I'm going to factor out and make that V1 over RT1 times P2 over P1 times T1 over T2 minus 1. I just did a little bit of algebra to put things in terms of a ratio there. And now I'm finally going to substitute in numbers into this entire thing. So I have 3 cubic feet, 500 psi. Psi is a pound force per inch squared. I'm going to convert that to feet squared. So there's 144 inches squared per feet squared. Divide that by, go to the tables and look up R. We're going to need an R. 5334 foot-pounds per pound mass degrees R times 530 degrees R. I'm going to go show you how to calculate that R in a minute. And then we have these final ratios that show up there, right? 2000 to 500 times 530 to 580 minus 1. For a final answer, I get 20.3 pounds. M2 minus M1. So there's the amount of mass that has been added to the tank. Okay, so I promised that we would go talk about this R, finding that R value. Alright, so let's do that over here. We're going to go to the tables. R is looking at these numbers. I'm going to use 15.45 foot-pounds per pound mole degrees R. Sorry, 1545, no point. Pound mole degrees Rankine. And then we have to divide that by the molecular weight of air, 28.97 pound mass per pound mole. Let's put this in the calculator. 1545 divided by 28.97 is that number over on the right. 53.33 is what I have in my calculator, and I'll be left with foot-pound force. Pound moles are going to cancel per pound mass degrees Rankine. Alright, so this is the R that we use there. Okay, so that completes one example only. And key to this was identifying this right away as a transient process so that we knew which equation to be starting with. We could also, the problem's not asking for this, but we could calculate how much mass entered, right? I guess that's what we got from the energy balance. Let's put that somewhere. The energy balance, what's coming in, right? The summation of Mn is equal to M2 minus M1. So conceptually simple with the conservation of mass, but some considerable work needed to evaluate the properties and finish this problem. Okay, so I'm going to stop the first lecture here, and we will begin the second lecture with an example of a steady flow device where we will apply a conservation of mass.